is our failure analysis lab. So mostly what they showed you in the video is what happens when everything's going right. You know, talking about testing everything, getting everything tested so we can ship the good products to the customers. Sometimes things don't go right and you have failures, so this is the failure analysis lab. Whether it is new product that we're bringing up, which we'll call new silicon when it comes in and it's packaged, or their reliability failures, or their customer returns. When those failures happen, we'll look at a sample of them and do analysis and find out what is this is part of the failure analysis lab. We call it the mechanical room. We'll do all of our mechanical deprocessing of the part. We physically deprocess, delayer the part by grinding or cross-sectioning so that we get to the location on the die or in the package that caused the failure, and we'll identify that failure mechanism. If the parts come in, it's a new design, maybe there's something with the design that doesn't work, the designers will be able to identify through the testing that's done on the test floor the suspect circuits. In the old, years and years past, when there was a design flaw in your silicon, it could take weeks. As you saw in the video, they mentioned it could take up to 18 weeks or so to get a design fix through the fabrication process and back out so you can test it. Well, here, with these tools, focused iron beam tools, we can do that in a matter of days. Say 2 days. We get the part prepped into the tool, we do the circuit edit, get the part out, and they can test it, validate that.
I should do remove bits. We can add bits as well. Add bits.
Well, actually, it uses a ion beam to mill into the circuit. We can cut, so we can cut off a circuit. We can reroute it to a different location. We can tie a signal high. We can tie a signal low, whatever it needs to be, so that we can adjust that. Now, after that, the whole part may not work, but for that portion of the test that we're interested in, and just debugging that circuit, we can prove that out. And then maybe they need to add some more elements in the design to really make the whole system work. These operations using these tools, with the small geometries we're using at 45 nanometer, 28 nanometer. These operations are extremely vibration sensitive. So at the threshold for the door there, the concrete is actually cut. In fact, all along these rooms, this concrete is isolated from the rest of the building to help minimize those vibrations. And also, just vibrations from the road and whatnot.
So in case of a quake, you can just screw up all your
Well,
job.
we are in Southern California, and we do have earthquakes. Luckily, in San Diego, the earthquakes are milder than they are, say, up in Los Angeles or in San Francisco. But we still have them. 45, 65, 150. Yeah, we'll do failure analysis on all those products here. This tool here, this tool will help us identify in the silicon where the failure actually is. This tool is a scanning optical microscope. It will use a laser to scan across the silicon, which we would have previously exposed. You scan across the silicon, and if there is, say, a short somewhere, you wouldn't know where it is until, as the laser scans across, it's locally heating. It's going to change the conductivity there, and it'll drop more or less current. This tool will sense that and show us where that location is, so that then we can go through and, as I mentioned in the other room, we can deprocess and find the physical mechanism that caused the failure to occur.
So diagnostics
But this one is not exactly set up for circuit edit, is more set up to do cross sections. So instead of using a polisher grinder to do a large area, in this tool we can do a very small, very precise cross section. We can also use it for some elemental analysis, and we can also use it for some probing. We have some probes that can go inside of the chamber. In this room that we're just going by, the one I'll fit in there, but it is a laser chemical etcher. It assists in the focused ion beam circuit edit operation. This poster is a good, gives a good description of what's going on. This is actually a cross-sectional view of a device and the silicon die. This is the substrate of the board. This was cross-sectioned in after this trench was made. So what we'll do is we'll use this laser chemical etcher to make this trench in the silicon. And we'll stop when there is about 5 or 10 microns of silicon remaining. The trench will be made over the area where we want to do the fib circuit edit. We would take this part and take it into the focused ion beam, take it into that tool, and finish the circuit edit. This operation takes maybe an hour or so to do this.
Hours.
Yeah, 1 or 2 hours. If we tried to trench out all of this using the focused ion beam tool, it could take over a day. So this operation was a large bottleneck. So with this tool, we're able to trench out a large section of silicon to enable us to do standard X-ray every 1/3 of a degree. Stop tool, build up that so we have some volume to look at. And we have cross-section good, the solder joints, gold bond wires that connect into the silicon die. We don't see the silicon because silicon is transparent to X-rays. Here we can see 2 bond wires touching, right? So that would be causing a failure. So all this we can do relatively non-destructively. To get these images as good and crisp as they need to be, we need to get the sample very close to the X-ray source, in which case sometimes we'll need to actually cut the sample down.
These are some different examples of certs that we have testing. This one is running Android graphics test. This one is running the Brew operating system and it's doing a data call test. And this one is also Android and it's doing a boot up test. So on each of these platforms, there are different projects. They allow us to do the basic functionality that you would do on a phone, just making calls and putting it out, maybe running games or something. We can swap the chip out in this socket here and test different devices. The goal basically is to correlate the software and hardware together as a system. You probably saw ATE, or you will be seeing it, I don't know if you've seen it yet. Their goal is just to test the hardware by itself in different circuits inside the chip. We add that software component and test it together.
So here you test software component.
Yes. All this testing on the bench here is done by hand, but we also have the capability to do automated testing. So behind me, I'll show you that. Run by hand. Because large quantity, we want it again to make it to the next one.
Basically, when parts come in, they're going to be checked in, and then they're going to bring them here and put the parts in the VLM. I think there's about 1 million parts right now in the VLM. So you can do it several ways. You can select from your actual parts. What I'm going to do is just bring a pan down. So if you're an engineer, you know where your parts are. Let's say they're in pan 15. You enter that pan, and it's going to bring that pan down. engineer or technician can come over, grab whatever parts they like. There is an RF reader in here. These will read the parts. So once they pull them out, they can come over here and say, confirm my parts, and it'll say what parts you have. And then you just have to verify that it's accurate. Say, yes, those are the parts I have, and then they'll go in. If it's in air, which happens on occasion, all they have to do is do a quick correction, and then they'll go through. Did you catch that?
So why is it so important that it works best on this, obviously?
So what happens is we didn't have it, all the parts were on the test floor.
Yeah.
So the engineers would keep on the tester, and it just became
So they have to keep in track of this.
You know, at the end of the day, hopefully the one takeaway you guys would have with this very large test floor with all these noisy instruments is really focused on giving, you know, hopefully you as a potential customer of Qualcomm or user of our devices, maximum experience possible. You know, if it's a video you're watching, hopefully the video quality is the best quality it could be. Maybe it's the voice quality or the audio of a phone call or music you're playing, the best quality it could be. And it's because of all these things are put into play to make sure whether it's the hottest of hot conditions or the coldest of cold conditions. People always ask, well, why do you test at 120 degrees, you know, say plus 85 or spec? Test all the way up to 120. Well, if you have a, you know, say a GPS device and your car is out in the desert and it's extremely hot, it still has to work, even though you're not making a phone call. Hopefully you're inside and staying cool. Maybe it's in the extreme cold.